Hello, statisticians. Here's your updated walkthrough for Lab 4. I'm going to see if I can record it in one part and give you a few more details to make this lab a little more accessible because it's a longer lab, as you can see, and it has a little bit of math in it. So let's get into it. As always, make sure you right-click and save this to a location that you can access later. And so I've done that, and now it's in our studio. As always, here's the outline for this lab, and you can use this outline to see where I am in the lab. If you're going to jump around in this walkthrough, you can better access where I'm working, and also you can minimize this to see a little more what's going on. So remember, put your name, update that. These little details, attention to details is important. This will help you be more accurate and make very nice presentations. So one of the objectives in this lab that we'll start with is illustrating this law of large numbers that we've discussed. So what is this law? This law says that as n, the number of trials of a random event occurs, the probability of a certain outcome that we've observed, the proportion of a certain outcome that we've observed approaches the actual theoretical probability of that event occurring. So if that's a lot of technicality to you, let's actually see this number illustrated. So what we're going to do in this next section is we're going to illustrate it using a sample function. This is a function that pseudo-randomly selects from a set of outcomes, and we can select sizes of samples as large as we want. So this code here says we're going to set the seed to 1. This means we're going to create a random number generator sequence that is the same for everyone. That way we can compare our results. So that we just leave there. The outcomes that we're considering are 0 and 1. They're nice outcomes because 0 could be tails, 1 could be heads. We'll use that kind of as our pattern. And then what we do with our next function is we sample from outcomes, sample size of 10, and replace equals true means once we sample ahead, we can still sample ahead again. We don't remove it from the sample. If I said replace equals false, I could really only sample twice because I'd first sample one of the heads or tails, and then I would sample the other one and then be done. So here's our random sample here. We got 10 trials of flipping a coin. We got tails first. 0 corresponds to tails. 1 is heads, tails, tails, heads, tails, 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 heads, heads. So that's what happened randomly. So let's use that to calculate the proportion of the times that head was rolled. So we had the proportion will be the number of heads divided by total number of samples. I'll put that in quotes so I don't make a new section. Notice the hashtag makes a new section. So that's what we're finding, proportion of heads. This is the formula we're going to use. So how many heads do we find in this sample? We got 1, 2, 3, 4 heads. And we had 10 items. So that's our proportion of heads, 0.4 or 40%. So what's cool now is we can increase the size. We had this number 10 here. Now let's increase the size to 100. And so here's the same bit of code, but now I've made the size 100. And what you could do is you could say sample equals here. That's just a lot of ones to count. It'd be kind of cool. I could actually use a table of my sample and tell me what happened. Here it says I had 49 tails and 51 heads. So what's the proportion of ones that I got? It would be 51 divided by 100. Or if you're fancy, you could say sum of sample, because all the heads count as 1. If I say sum sample, that's 51. So I could do it that way too if I didn't look at the table. So it tells us that 51% of this sample of 100 flips was heads. So now what we're going to do is we're going to keep sampling with increasing size up to 1,000 and 10,000. So here's 1,000. That should say 1,000 here. So with 1,000 samples, we had 502 tails and 498 heads. So that's what we got for the proportion of heads on 1,000 samples. And so, and we can also do it with maybe 10,000 samples if we want. This is just optional, but I want to illustrate this to you. I'll copy this code and say, what if I do it with 10,000? If I do it with 10,000, $516. 1/6 divided by 5,016 divided by 10,000. So tell me what you notice as these numbers, as this number of samples gets bigger and bigger. Say what you see happening here. And if you want to see a visual example of this, this runs a simulation of increasing sample sizes, and at each new flip, it updates the proportion of outcomes. So let's just look at this. You don't have to do anything with this code. We just want to see what it looks like. This makes the function that does all the work. Here's actually where I plot the function. Notice when I run that, nothing happened. So if I plot this function now, it tells me as n increases, we got n up to 2, 5, 10, 20, 50, 100. The number of proportion of heads looks like this. It gets higher, lower, higher, lower, higher, lower, but it gets closer and closer and closer to what we would expect, the 50% here. So that line represents the theoretical probability of heads. And so let's run that again, but now let's use 10,000. So I'm going to make the number of samples n 10,000. It's going to take a little bit because we're doing 10,000 trial flips. And you see this line here gets closer and closer and closer to 50% as we go on. So that's a really nice illustration of the law of large numbers. So you can restate what the law of large numbers says here and why or why not this illustrates that law of large numbers. So now that you've seen it illustrated, basically what you should do is go back and look at this definition. Here's what the law of large numbers says. You can put that down here. So if I was on this section here, you could say the law of large numbers says this, and oh, that was the wrong place. Large number says this, and this say the above graph illustrates this. And then talk about the properties of the graph. What's happening to the proportion of success? This is getting bigger and bigger. Okay, so that's our first section. We got a good example of the law of large numbers. This is the basis for probability because we want to know with some kind of accuracy what the chances of things are happening. And so another example would be rolling a dice. Let's run our simulation for rolling a dice. So here I've illustrated the probability of rolling a 1 when the outcomes are 1 through 6. And I've said the theoretical probability of success is 1/6. So this line here is where 1/6 is. So you can see, did these results follow the law of large numbers? Why or why not? That's a cool example. Okay, so next, take a break if you need to, but I'm going to keep going to try to make this video all in one go. Now that we have understanding of probabilities of events, now we can talk about the probability of multiple events occurring. And the first and easiest way to compute multiple events is when they're independent. When they don't affect each other, we say those events are independent. And so when two events are independent, draw this, here's the rule. The probability of A and B occurring is probability of A times probability of B. That's a very nice rule. Oh yeah, that's written down here. So we're going to use that rule as we go on. And so let's look at the probability of flipping heads twice. Okay. That's probability of flipping heads and heads. Okay. That's, according to our rule, the probability of flipping heads times the probability of flipping heads. Okay. So each one of those is 1/2, right? So we get 1/4, the probability of flipping heads. So there's a 1 in 4 chance of flipping 2 heads in a row. So how does that extend if I say heads and heads and heads? 3 times I have to do heads. We can use that rule like this, multiplying the probability of heads 3 times now. So that's 1/2 times 1/2 times 1/2 equals 1/8. So I think you see the pattern now. By the time you get to 10 heads, the probability of flipping heads 10 times is the same thing as the probability of heads times itself 10 times, which is the same thing as saying to the 10th power. I'm going to use some code to do this. Let's say 1/2, my code chunk, 1/2 to the 10th tells me what that probability is, and you can see, oh, it's a pretty small number. 1/2 times 1/2 times 1/2, 10 times. So that's our first rule, independent events. Let's go on to our next rule. When we have complementary events, what are complementary events? Complementary events are like either or. Either I flip heads or I flip tails. They're complementary. We can't have both at the same time. And if I don't flip heads, that means I flip tails. That's a good example of a complementary event. So the notation for a complementary event, if A is an event, we say the complement of A is A complement. So using my heads and tails example, I could say the complement, oh, that's not a good color. The complement of heads is tails. That's how I would write my notation for complement. And the complement of tails is heads. So what's really useful about complementary events, if you like taking notes, is this formula here. It's kind of hard to see in R, but if I put my cursor there, it tells me that the probability of A complement is equal to 1 minus the probability of A. Very interesting. Or another way to write this is probability of A plus probability of A complement is 1. This means if I add up 2 complementary probabilities, they always add up to 1. This is because I've counted for all possibilities. Either A happens, either A occurs, or A does not occur. And I've accounted for all possibilities. So this rule is nice for finding probabilities that are often harder to find without using this rule. So suppose I flip a coin 2 times. What is the probability of flipping at least one tail? That right there looks like kind of a mess. If you've got some math hesitancy, you might try running from this problem, but don't. I'll make it easy, okay? So if we want to know A is the probability of flipping at least one tail, just write that down. That's what we want to find. We want to find this probability of A. Just set it up like that. This answers our question. What is the probability of flipping at least one tail? Well, we want to find P of A. Okay. Well, we know P of A equals 1 minus P of A complement. So if we can find A complement, sorry, A, this is like superscript symbol C. So A superscript C is an easy way to write it. If you use print dollar signs, it makes it look nice as a math formula, but either way, you can see what I'm writing. So what is the complement of flipping at least one tail? This is what this problem boils down to. So the probability of flipping at least one tail, the complement of flipping at least one tail is flipping no tails. See if you can convince yourself of that. Either you flip one or more tails or you flip no tails. One or same thing. So, and I'm going to make you a note here. If I want to make these start on new lines, when I knit it, these will jam together. So if I put 2 spaces at the end, now you can knit it, and this is always good to do periodically. You can knit your code and see that it looks like what you want it to look like. You also, if you found any errors, you'll catch them sooner. So you're not looking at a whole document of errors, but hopefully just a few. So no errors. Now I can review. I was working on complementary events. See, these are on separate lines now. Makes it easy to read. It's a little trick. Okay. Or you can always put a new line in between them and then it'll put them on new lines. Okay, so we now just want to find 1 minus the probability of no tails. Well, no tails equals all heads, right? And we previously found the probability of flipping all heads. Flipping heads twice in a row is 1/4. So we just say 2 minus 1/4. So there's a 75% chance of flipping at least one tail. So difficult problem, but we boiled it down to just some simple steps. So now you get a chance to practice these same steps with 11 and 12. So I'll do 11 together with you, and then I'll let you figure out 12 on your own. So probability of at least one tail using the rule of complements is 1 minus probability of no tails, or 1 minus the probability of all heads. That's what we're going to use to solve this one. So I'll just say 1 minus probability of all heads. And if I'm flipping 3 times, that's just 1/2 times 1/2 times 1/2, or 1/2 to the 3rd power. So there's the probability of flipping at least one tail. So that's pretty handy dandy. See if you can figure out 10 yourself. Should be pretty high probability. Then when you're ready, we're going to go on to expected value. Okay. So expected value, very useful concept that describes the way of evaluating the value of a decision with multiple outcomes. So if I'm going to do something that has 2 different outcomes, and each outcome has some kind of value I can measure, I can use that to calculate what I would expect to gain if I were to repeat this process many, many times. So it's a probabilistic concept that allows us to put value on choices. That helps us make better choices. So we'll see, is it good to buy a raffle? Is it good to buy insurance? Is it good to gamble? These are all questions that expected value can help us answer. So this formula for expected value here, I'll write it out because that's kind of a good way to talk about it. Expected value, I often write it like that, is the value of A, that's the value of A occurring, how much money I would get if A occurs, times the probability of A, that's the probability. Then I add the probability, the value of B times probability of B. Okay, so see what we're doing. And so if I want to find the expected value, all I have to do is find these 4 things. See if we can do that. And examples, the examples will make us nice. Oh, and you can see what I've done here. I've kind of scaffolded the problem for you. I said, hey, we're finding the expected value. So if my event A is win and B is lose money, that's one way to frame it. Okay. So if I find these 4 things, the value of winning, the probability of winning, the value of losing, and the probability of losing, I can just use this formula here to calculate it. So let's look at the situation. Hope you can see that this formula here is the same thing as this. I've just now considered that A is winning. So if A is win, what is the probability? Well, I should just say it this way. What is the probability of winning and the value of winning? If I win this raffle, okay, this is a raffle. You purchase tickets for $5. 1 out of 2,000 tickets will win. And whoever wins gets $4,000. So the probability of winning is going to be 1 out of 2,000. There's only 1 out of those 2,000 tickets that you can win. The value of winning will be 4,000 if I win. But remember, if I won, that means I also bought a $5 ticket. So this is kind of the catch. We have to subtract 5 here. We paid $5. So really, we win 3,995 is our net win. That way. So now I want to look at the probability of losing and the value of losing. You can figure those out. Probability of losing is the complement of the probability of winning. So I could just say 1 minus using our rule of complements. And the value of losing, we lose $5, so we're going to have to say -5 because we are. I'll just say negative represents money lost. Get that money. Okay, so now we can plug these numbers in here. Value of winning was 3,995. Probably winning was 2,000. Losing was -5. And this ends up being 199 out of 2,000. Okay, so now we can use that. And this, if I run this code, it'll store all these values and then output this. So all these values became something, and now I know my expected value is -3. When I forgot something, since these are butting up to each other, I have to put 2 spaces afterwards. Otherwise, they will put them on a new line. Okay. 3. So this means, on average, each person is giving about $3 to charity. That means like every ticket, the average loss is $3 for the person that's buying it, but for the charity, they're getting $3 per ticket, which is kind of cool. You could also find the total gain for the company this way. They did $5 per ticket times 2,000 tickets, not 2,000 tickets. What is it? Oh yeah, 2,000 tickets minus $4,000 for the win. And so, oh, that's not actually a code chunk. That's the total gain, right? And if you divide that total gain, 6,000 by 2,000 tickets, that tells you the average gain. So it's the same thing as expected value, just another way to think about it. So that's kind of cool. That's expected value. I'll let you work on the earthquake insurance problem on your own. See if you can figure that one out. And don't forget that if you do collect insurance, you still paid for a $100 premium. Okay. So that's what we got for earthquake insurance. And our very last topic covers conditional probability, which we'll use for doing something called Bayes' rule. So Bayes' rule. Oh, no, I've made that optional. That's just kind of a long, detailed rule that's a little more complicated. So for now, we'll just use it for finding conditional probabilities. So the formula for conditional probabilities comes up when we have events that impact each other. So conditional, you could see, is the opposite of independent. Independent means they don't affect each other. Conditional means they do. So 2 events are related. So when two events are related, we have to be a little more careful for finding probabilities. So what we do is we find out the probability of two things. Probability of A, we write a vertical line B. This means the probability of A occurring given that B has already occurred. Knowing that B occurs gives us more information, and that can change the probability of A occurring, as we can see from like a two-way table. We'll see that in a bit. So this is something, instead of probability of A times probability of B, this is the formula before. Now we have to modify it. Okay, so we're gonna use that formula. This is the formula we want to use right here. And so actually you can take this formula and rearrange it, divide by probability of B, divide by probability of B, and you cancel those out and get this formula. So that's also a formula we can use. So we're just going to check it. We're going to check it with a situation where we had a machine learning. This is an algorithm the computer uses to try to predict what different events are. So if we look at this figure in our textbook, 312, it's also in lab 4. I pasted it here. What's going on is we got two things that can happen. This computer or algorithm is trying to predict whether a photo is about fashion or not. That's important because then I can use it for giving ads or controlling your minds, essentially is what it boils down to. So if a computer can do that, if they can predict what your pictures are about, or facial recognition uses machine learning, we can consider it this way. Either the machine is going to predict about fashion or not, or there's a reality. We can check. We know as humans whether maybe we categorize it. The truth is something we categorize as the photo is about fashion or not. We'll say that's some kind of objective statement. Okay, so here's our table, and we can find things like what is the probability of predicting fashion given the truth is not about fashion. That would be a mistake, right? If it predicts fashion and the truth is not about fashion, we want to know what's the probability of that happening. So this tells us already will assume given truth is not fashion, the way we can look at this is we circle this right here. We know this has occurred. So we've narrowed down our cases just to the truth being not about fashion. And we're saying of those cases, how many times is the machine wrong? So given that the truth is not fashion, the probability of predicting fashion is 22 out of 15, 13. So that's the kind of thing we could answer. So let's go through some questions in the lab that do this, and we actually will then check whether or not our formulas work. Okay, so back to the lab. We're going to find this. We're going to find out, using our formula, what is the probability of machine learning predicting fashion given that the truth is fashion? So let's use our formula. If A is machine learning predicts fashion and B is the truth is fashion, probability of A given B, A and B is the total number that are about fashion and predicted fashion. So back to here. This is A. I gotta draw here. This is A and this is B. Probability of A and B is going to be 197 times total both occurred out of the total 1822. So 197 divided by 1822. Okay. And let's find out what the probability of B is. Because we can use our formula now. Probability of A and B divided by probability of B. If we can find out that, then we can find out our conditional probability. So probability of B is the probability of being about fashion. So back to here, we're looking at what's the probability of any photo being about fashion. So this is B. Whoops. This is B here. Probability of B is 309 times the photo is about fashion out of a total of 1822. So that's the probability of B. 309 divided by 1822. So now we can use our conditional formula, probability formula to say, hey, probability of A given B, probability of A given B is probability of A and B right here. It's A and B just to be clear. Divided by probability of B, and that will be our conditional probability. Cool. So that's something that our formula tells us. But now we can also check it the way I did before. So what's the probability of A given B? Back to our table here. I'm going to find the probability of A given B. Well, given that B has occurred, we're only looking at these cases about fashion. So there's 309 total cases. And so the probability of A occurring, predicting fashion, given that B has occurred, we're looking at just these cases, 197. So let's check that. It's 197 over 309. That's what I got. And we see we get the same thing. So this is like kind of a big mental exercise, but in the end, we'll want to check all our answers using two different methods. And if you can do this, that means you have a pretty good understanding of conditional probability. So how about I do one more together? And then by that point, hopefully you can figure out the rest of these. Okay. So I want to call probability of ML correct given not fashion. Okay. So A is ML correct. B is not fashion. So I'm going to do it like this. A given B. So now my probability of A and B is going to be the probability that both ML is correct given that it's not fashion. So we know not fashion is going to be happening. And in which case is the machine learning correct? When it predicts not fashion. So the probability of A and B is going to be 1,491, 1822. Okay. Now let's look at the probability of B. Probability of being not fashion. Not fashion would be just these cases here. Here. So how many are not about fashion? Is 1513 divided by 1822. So back here equals 1513 divided by 1822. And now probability A and B divided by probability of B gives us the conditional probability So here we're finding, and I'm putting spaces after so it formats nicely. There we go. So we got a 98% of being correct. Guessing not fashion. We're guessing not fashion correctly. Okay. And I'm just going to check that. Again, I'm looking at the chance of predicting not, given that it's not about fashion. So I could also think about the problem this way. I already know it's not about fashion. Given that I already know the photo is not about fashion, I know it's just these cases. So the machine learning is correct. 1940, 1491 out of 1513. I have to do some erasing here. 1941 out of 1513. And so that gives us a very good way to check our previous answer. So 9, 14, 91, 13. Same way to do it. So really now you have two ways to find conditional probabilities using our formula or going directly if you have a two-way table. So now I'll give you a chance to practice with these two. And we'll see you in class. Please let me know if you have any questions or suggestions for improvement of any of these materials. I hope they're helpful. Good luck.